I wanted to share a little trick that I use to remember the functional form of a Fourier transform. So if you remember, what we have is f of t, okay, multiplied by a complex exponential term, and all of this integrated over time from negative infinity to infinity. And what this ends up being then is the expression for a Fourier transform of this function f of t evaluated at a given angular frequency omega. And so what I wanted to share is an intuitive sort of understanding of what the Fourier transform is doing from an engineering perspective. And so some of the steps here are going to be sort of mathematically non-rigorous, but it does help me understand what's happening with the Fourier transform so that I sort of have an intuitive feel. Okay, so starting off, what we'll write down is, let's assume we have two vectors. Okay, and what we'll do is we'll write down the components of these two vectors. The first vector is this, and the second vector is b. And so these two vectors have basically identical dimensions. They have a total of n terms each, okay, capital N. And so what we'll do next is we'll take the dot product of these two vectors. And if you remember, the dot product of two vectors basically is an expression of how similar these vectors are to each other. Okay, how similar are A and B to each other in the mathematical sense. So for example, if we had the two-dimensional case, and we had a first vector looks like this, and then if we had another vector B that is sort of lying almost right on top of it, then you would expect that the dot product between these two vectors would be relatively large. Whereas if you had another vector, say A prime, and then you had a B prime that is at a 90-degree angle to it, then in the mathematical sense, these two vectors are not really similar to each other. Right, so the similar case would be when they're right on top of each other, whereas this would sort of represent that they're not similar, they're orthogonal in the mathematical sense. Okay, so then going back to the dot product, the way that we compute a dot product is that we sum over all of the dimensions of the two vectors, term by term, an times bn, and then we remember to take the complex conjugate of one of the terms. Okay, so this is basically the computational expression for determining the dot product of two vectors. But basically what we're trying to do is to figure out how similar these two vectors are. Okay, so now going forward to the Fourier transform, what we have in that case is if we have one vector being a first function, and then we write down the components there, it would be f of 0, f of 1, and so on. Okay, and then we have another function which is the complex exponential. Okay, and then so we also write out the components of this function. Okay, so what we have here are two functions that we're expressing as vectors. And if you remember, this term here is a complex exponential at a given frequency omega. Okay, so if we ask the question of what is the frequency content of the function f of n at the frequency omega, then really another way of looking at this is to see that this is the same question as how similar are fn and the complex exponential of frequency omega to each other, right? Because this term is really representing the frequency content at a given frequency omega. And so when we put the question in this way, then what we can see is this is really it really calls for a dot product to be used to answer this question. So that's exactly what we'll do is we'll go ahead and take the dot product between these two functions. Okay, and so writing out the computational form of the dot product, okay, we go over the indices, and then it would be f of n times e to the j omega n, but that has to be taking the complex conjugate of. And so what we end up with is, okay, we basically introduce a minus sign into the exponential term. Okay, so this now ends up looking very, very similar to our definition of the Fourier transform, except for the fact that this n is now discrete. But what we want to do is we want to make it continuous. So what we would do is replace the n's with t's, and instead of doing a summation, we will do integration. Okay, so what this ends up becoming then is an integral of these terms, okay, of these sort of term by term multiplication, but now in the continuous time case. Okay, so what we've done here then is basically we've rederived the actual expression for a Fourier transform. So if you look at it again, what we're seeing is that this is the function, and it's now a continuous time function, and this is the complex exponential function. And really the question that we're answering by performing the Fourier transform is, what is the similarity between f of t and a complex exponential at this given frequency? And so that is basically computed using the dot product as our tool.